Hello kids, this is the third lecture in the series Basics of Chemical Bonding. Previous two lectures, many views I got, but I forgot one thing, that please subscribe the channel. If you like the video, hit the like button, okay, that is much needed, and it keep on going till the JEE Main second attempt, and we'll try to cover all the entire chemistry through these videos later till the second attempt. Okay, every day I will try to put at least one or two videos every day. So, and I will not consume much of your time, hardly 1 hour, or you can see the just important key points of the video. Today I have changed some strategy. Okay, so there will be no writing. I have just pre-done the entire lecture and I'll just explain it. Okay, so yesterday we have covered that stick number till stick number 5. Now we come to stick number 6. So stick number 6, as you can see, stick number 6, bond pair, A case, 6 bond pair. 6 bond pairs will be arranged to minimize the repulsion in such a fashion that the resulting geometry we got is called octahedral geometry. This tool I generally use in the classroom to explain the octahedral geometry. This you can also make with a simple paper and pencil. Okay, so the octahedral you can imagine like this: 1, 2, 3, 4 bonds. This is the 5th one and this is the 6th one. Got it? So all bond angles are 90 degree. Understood? Suppose we count how many 90 degree bond angles are there. So there will be 1, 2, 3 and 4. 4 above the plane, 4 below the plane, 8 and 1. This is the 9th one, this is the 10th one, this is the 11th one, this is the 12th one. So there will be 12 such 90 degree bond angles. Understood? So there will be 12 90 degree bond angles. So there will be 12 such angles. 12 such angles. Nowadays in the integer answer questions they are asking these such type of questions. Okay, so it is a symmetric. Understood? Symmetric means all bond angles are exactly same. Sometimes people think that we can measure 180, but 180, if all 6 bond pairs are there, the 180 bond angle cannot be measured. Although the mathematical approach, if we apply, we can say these are the transposition, this and this are the transposition, so the bond angle is 180 degree. Similarly, this and this are the transposition, and this also are the transposition, so these angles are 180 degree. Got it? Now the second case, if there are 5 bond pair, if there are 5 bond pair and 1 lone pair, so what I have done, basically I have done this thing. See this? Understood? This thing. So it is like an umbrella. So here is the lone pair and this is the bond pair, and 1, 2, 3, 4 and 5th one, 5 bond pair. Here is the lone pair. This is the classical question asked in JEE integer answer question, and why it is called classical mistake of the IIT, that they have given 2 answers, both the answers correct. Actually everybody awarded marks for this question, that how many 90 degree bond angles are there. So there are no 90 degree bond angles. 0. Answer is 0. Okay, so bond angle you can measure 1, 2, 3, 4. Okay, 4 in the plane and 4 below the plane. 8 angles will be there, but out of 8 angle, none will be the 90 degree. Reason being for this, the lone pair is here, it will suppress these 4 bonds. Okay, so they will slightly incline towards this axial position, slightly inclined. when they incline, this and this will incline, the bond angle between them cannot remain 90 degree. It will be less than 90 degree. So all the 8 bond angles will be less than 90 degree. This is very important thing to understand, that none of the bond angle is now 90 degree. They all are less than 90 degree, depending on the relative position of the atom and relative size of the atoms. So bond angles are less than 90 degree, all 8. Understood? And the name is called square pyramidal. This octahedral can be known as square bipyramidal. Square bipyramidal. Okay, another name for this could be square bipyramidal. So there is a base of square. There is a square base. Understood? Square base, and triangular face, triangular face, triangular face, triangular face. So there are 4 triangular face above the plane and 4 triangular face below the plane. So there will be 8 triangular faces. That's why the name given octahedron. There's a difference between octahedron and octahedral. Octahedral is the geometry, but octahedron is the shape. Understood? Octahedron is the shape. And here the shape will be square pyramidal. Okay? Shape will be square pyramidal. Now, next case. The next case is 4 bond pair. C case. 4 bond pair and 2 lone pair. Okay? 4 bond pair and 2 lone pair. Now, what to do? These are the position for the lone pair, blue color. These are the position for lone pair. Bond angle will be exactly 90 degree, and the shape is called square planar. Here the point to remember is what? The point to remember is the lone pair must be in transposition. Lone pair must be in transposition. Transposition means opposite to each other. Transposition means opposite to each other. What is the meaning of opposite to each other? So suppose one lone pair is here, means another lone pair must be opposite to it. And you can use any position. All position are equivalent. If you can put one lone pair here, another lone pair here, again it will be a square planar. You can put one lone pair here, another lone pair here, again it will be a square planar. In each and every case, it will be a square planar. You can put 2 lone pairs. To minimize the repulsion, they must be trans to each other. They cannot be cis, 90 degree to each other, because repulsion will be more in the case of 90 degree separation. So the repulsion is minimized. This is the basic concept of VSEPR. The geometry, the molecule always adopt such a geometry where the repulsions are minimized and molecule is maximum stable. Understood? Okay. So this is all about the stick number 6. Now stick number 7. Stick number 7 is very important, as well as you have to memorize the species. You have to memorize the particular species, because there are not so many examples. For remaining stick numbers, I will take example once I finish hybridization. So we will take examples including hybridization as well as VSEPR applications. Okay. So for stick number 7, I am taking the example along with the different case, because there are very few limited example for every case. Stick number 7, first case, suppose there are 7 bond pairs. So 7 bond pairs, they will arrange themselves in a regular pentagon. There will be a regular pentagon in a plane. We call it equatorial plane, and bond angle will be 72 degree each. Understood? From the basic geometry, we can easily tell that if there are 5 bonds in a plane, then there will be a regular pentagon, and regular pentagon, the internal angles will be, these angles will be 72 degree. Got it? Now there are 2 axial position. So There is a pentagon in this plane and axial position. So from this plane 90 degree, 90 degree. It is again a asymmetric, like TBP, diagonal bipyramidal, that was asymmetric. It is also asymmetric. So equatorial plane bond angle 72 degree each, axial 90 degree and 90 degree 7 bond pair. The very well known example, limited 2 or 3 examples are there for this. So for our well known example is IF7. IF7 is the example for this case where pentagonal bipyramidal. So name is pentagonal bipyramidal. Pentagonal bipyramidal. Bipyramidal. Pentagonal bipyramidal. In short, we'll call it PBP. P for parrot. PBP. Got it? So it is stick number 7. Now, next, B case, 7 bond pair, 6 bond pair and 1 lone pair, most important case. The example is also from an NCERT example, XCF6, xenon hexafluoride. Okay, so basically we are talking about xenon hexafluoride gaseous. It is very important thing, it is gaseous. Because in solid state, its nature is structure and its nature is different. So we are talking about gaseous state, xenon hexafluoride, or you can say the liquid state also, the same thing. So here xenon is surrounded by 6 fluorines. Xenon is surrounded by 6 fluorines. I am using different color for this. First fluorine, second fluorine, you can say these are the along the axis. Now equator, 4 fluorines along the equator. 4 fluorines along the equator like this. Got it? So 6 fluorine are arranged like this. It is an octahedron obviously, but there is 1 lone pair. So there is 1 lone pair. This is the delocalized lone pair. It is delocalized lone pair. What is the meaning of delocalized lone pair? Lone pair is not fixed. What is the meaning of fixed lone pair? In the previous case, stick number 6, 4 bond pair, 2 lone pair. These lone pairs are localized. They are fixed at their position. They will not move. Similarly here also, this 1 lone pair is localized. It is fixed. Its position is fixed. It will not go anywhere. So these are the localized bond pairs. But here, bond pair is delocalized. How it is delocalized? Pointed towards either, there are 2 possibilities, pointed towards either edge center or face center of octahedron. So this lone pair, I can draw one more diagram without writing the C. Xenon here. Okay, so we can draw a face. This is the face. So the center of face will be here. The face center will be here. So either lone pair is pointed towards this face center, or this lone pair may be pointed towards this edge center. This is the edge center. So these are the position 1, position 2, you can say position 2, and this is the position 1. Position 1. Okay, so it may found at 2 different positions and it keep on moving. Okay, it keep on moving continuously either at the edge center or the face center. Is it very important to memorize this information? Very important information. This lone pair is delocalized. Okay, regarding this dipole moment, we'll talk later on, not right now. Okay, is it clear now to everybody? All 6 fluorines in octahedral fashion, and there is a lone pair which is not localized, which is delocalized. Mind it, you cannot say, sir, I will use VSEPR and I will do like this. There is a regular pentagon, there is a regular pentagon, and I will put lone pair here. Okay, then it will be pentagonal single pyramidal, yeah, pentagonal pyramidal. No, it is wrong structure. It is not found, not proven experimentally. Experimentally, it is proven that it is distorted octahedron. Distorted octahedron. Got it, everybody? Now, there is one more thing to remember regarding this molecule. Let me finish it here itself. In solid phase, XEF6 exists as XEF5 plus cation and fluoride as anion. This is important information again to memorize. Okay, in solid state, XeF6 exists as XeF5 pentafluoridoxenon cation and fluoride as a anion. Okay, so if we apply VSEPR here, then we can decide its geometry also, and that will prove the gas phase structure of this molecule. See, so here I will use some counting, and that counting you can learn, or again I will repeat it. 19, 18 and 19. 19. So XeF5 plus cation. Okay, how to decide the stick number? In order to decide stick number, we have to use the valential electron of central atom, that is xenon, least electronegative obviously. So valential electron of xenon is 8. Due to positive charge, 1 is lost, so remaining is 7. Understood? There are 8 valential electron in xenon. Due to positive charge, 1 electron is lost, so there will be total 7 electron. Okay, out of 7, 5 will be consumed by fluorine, because each fluorine will require 1 electron to complete its octet. So there will be bond pairs 5 bond pair. And how to decide lone pair? Lone pair, we can decide lone pair must be equal to 7 minus 5 used by fluorine divided by 2, that is equal to 1. By 2, because we have to decide pair. Pair means 2 electron, that's why divide by 2. So there will be 1 lone pair, understood? So 5 bond pair, 1 lone pair, that is the 6, stick number 6. So stick number is 6. For stick number 6, what we have to do? Again, we have to do like this, xenon, and there is a lone pair. Understood? Now nearby, it is a cation basically. It is a cation, and nearby there is a anion, F minus. When this anion approach to cation, now you can easily understand what will happen. When this anion will approach to cation and they will form a discrete molecule in gas phase or liquid phase, then this lone pair will be repelled slightly and it will be delocalized, and we will obtain the resulting shade of the XeF6 that we have done here. I think it is, yeah, that's we have done here. Understood? You will get the same geometry. When the 6 fluoride approach, 1, 2, 3, 4, 5, when the 6 one approach, it will make a bond, okay, by donating its lone pair in the vacant orbital, and the lone pair will repelled and it will be delocalized either towards edge center or towards the face center. Okay, so it will help you to understand this geometry also, why it is distorted octahedron. The last case of stick number 7 is Stick number 7, last case, C case. C case is what? There are 5 bond pair and 2 lone pair. 5 bond pair and 2 lone pair. B case we have done 6 bond pair, 1 lone pair. The last case is 5 bond pair and 2 lone pair. How to deal it? 5 bond pair, 2 lone pair. It's very simple. So we have to draw like this. There is a regular pentagon, and there will be 2 lone pairs transposition, because the maximum separation for the lone pair will be 90 degree, not 72 degree. The lone pair cannot be in the equatorial plane. Reason, separation is less. So lone pair will be trans to each other, 90 degree separation from the plane. Then the molecule or species will be stabilized, minimum repulsion, maximum stability. Okay, the well-known example for this is example XEF 5 minus anion. XEF 5 minus anion. Okay. So suppose you want to apply the VSEPR concept that I have taught you, right? Like this, you can apply here also. Okay, xenon outermost 8, due to minus charge. Due to minus charge, there will be one more. So 8 plus 1, 9. Out of 9, 5 will be consumed by fluorine. Got it? So out of 9, 5 will be consumed by fluorine. Remaining 4 will make how many lone pairs? 2, obviously. 4 electron will make 2 lone pair. Okay, so you can count on the fingers. Whenever we decide stick number, it can be done on the fingers itself. Understood? So very simple case. So this is the end of our VSEPR theory and all the stick numbers explained properly. Now we come to the next part. Then we'll go for multiple examples. Okay, here the bond angle are 72 degree, and we call it planar pentagonal. Planar pentagonal.